like to talk about some interesting discrete time systems. In this particular case, two different ones that are IIR systems, not FIR systems. And you can immediately see that because, well, there's a y sub n minus 1 connected to y sub n, and you're thinking that looks different than a typical FIR system if you're used to FIR systems. All right, so how do we start to analyze it? Well, we want to take a look at this and actually analyze and take the structure and say, well, I can take this into a z transform, group some terms together, and I get this transfer function. Interestingly enough, this transfer function is now rational in the sense that I've got a polynomial in the numerator and a polynomial in the denominator. Great. So now I want to say, well, what does this start to look like? Well, the first thing I might ask is, well, what does the impulse response look like? And so let's think about that for a second. Well, I'm going to look at this and remember there's a few things out of Z transforms that we started to know. And this is actually a pretty typical and more powerful way to often work with Z transforms. If you've only looked with Z transforms for like FIR filters or transforms just for FIR filters, you're probably thinking, well, it just seemed like a redundant thing. But now it becomes kind of interesting because now I can do some interesting simplifications, move this rather interesting difference equation to Z domain, and now I can do some interesting things. Well, Z domain, of course, because I knew the delay properties, I could move that. But interesting things like the delta function. So a delta function transforms to a 1. A step function is 1 over 1 minus z to the minus 1. And if I have a to the n, I get u to the n. And then I get a 1 over 1 minus a to the z minus 1. These two things sort of can come about even from looking at an FIR filter. But FIR filters say for a boxcar response and then taking it to almost an infinite length. And what I find is I get these kinds of functions when I'm done. This is cool because what it says is that if I can find certain rational things in Z, I can immediately transform them back into things that I understand and things that make sense in the time domain. So this becomes a very useful transform. So how does this work here? Well, notice I've got 1 plus z to the minus 1 over this. Well, if I'm doing an impulse response, that's just a straightforward simple function. That's just 1. 1 is pretty easy to work with here. And then I can take this and go, wait, I can inverse transform this. I've got a 1 and a z to the minus 1. That gives me a 0.9 to the n and a 0.9 to the n minus 1. Delayed over n minus 1 time. And you're like, this is really cool. Okay, I can really solve this. In fact, what's interesting is if I look at that for that first transfer function, this is in fact exactly the response I would get. So you get the sort of initial output goes to 1. Once I get the second part, it kicks up to 1.9, and then it rolls off roughly, because a little bit every time. In fact, this feels like an exponential. And so if you're looking at these sort of approaches, you're thinking this feels like the way we might solve things with differential equations and Laplace transforms. It feels like the kind of time constant structures, and in fact that would be correct. This is exactly how you want to think about these structures. An interesting thing is you can then say, what happens for u of n? Well, that's still not too bad. Now I take all of this and I multiply by 1 minus z to the minus 1. Well, remember, I know I have this transform underneath here, so that's what I'd want to come up with. Okay, if I can do that, that's great. Well, how do I do it? Well, you might remember, say, maybe from calculus and other places where I can take sort of rational functions and then separate them into sums of things, right? Partial fraction expansion. Not necessarily everybody's favorite technique, but it is a very useful technique. And it turns out for this structure, you can actually do a partial fraction. You can solve for a and b, and as a result, you actually get the resulting step response. Which is kind of an interesting sort of response that you get. Certainly starts off at u of n, and then it continues to kind of grow over some time as a result of the step response. So it's really quite cool what you can actually get out of this. You could even take a second case. Here's a second differential equation. Now it's a subtraction here. And what I could get is I get the same structure h of c. I can then transform it and get its impulse response. Notice here it's all zeros, and then it pops up, down, and then sort of has this very fast drop to 0. This is very cool. Again, same sort of thing, but it can alternate across the 0 axis in this case. And so again, neat response, right? We'll take it one step further and say, well, what happens if I look at the step response? Well, it's 1 over 1 minus z to the minus 1. I get a 1 minus z to the minus 1 because of this difference. And guess what? then those two just subtract out and I get actually this very straightforward term which then tells me exactly what the step response would be. And so just some very, very powerful techniques of what initially looks like pretty scary kinds of equations at first if you're not used to it. The same sort of thing could be said if you're solving linear differential equations. You're like, well, how do I solve it? But this actually gives a straightforward formulation using type of transform theory to make this work.